Hi all, my name is Ansi Susan Matthews and I am an OMS CS grad student and I'm doing cyber physical security as my sixth subject. And the paper that I've chosen today to present is Algorithmic Attack Synthesis Using Hybrid Dynamics of Power Grid Critical Infrastructures. This paper, I'll give a few details about the paper. The authors are Shenki Huang, Sriharsha Etegoni, who is from the Rutgers University, Louis Garcia from the Brandman University, Sayan Mitra from the University of Illinois Urbana-Champaign, and Saman Aliari Zoners. And this was presented on July 2018 at the 48th Annual IEEE International Conference on Dependable Systems and Networks. So let's go into further details. The content includes an overview of why an algorithmic approach was used. We look at the threat model and the hybrid model analysis, the algorithmic attack synthesis which was used for the transient attacks, and the results of the transient attacks, and the conclusion. So here we are actually going to look at few examples of critical infrastructures. So which are the cyber physical critical control systems? You can look at the examples. We can see that water treatment, factory automation, electric power grid, and nuclear reactor. These are a couple of cyber physical critical control systems, and they are very critical for the infrastructure of any nation. So in our paper presentation, we are actually going to look at how the electric power grid is requiring effective cybersecurity and protection systems simultaneously. So if you see, there have been many multiple ideas from cyber security research. They have actually been deployed currently to keep adversaries out of the critical plants and control systems. But those alone are inadequate. So if you see, why is security critical for a power grid? We might have read about multiple news through various channels where we see that these systems have been attacked. So if you see, an adversary's primary objective is to maximize physical impact through stealth. For example, if they actually target an electricity grid, we know what can happen. The impact could be huge. They could bring down power transmission lines, leading to outages. We can also see that since they are the cybersecurity solutions which are currently present are irrelevant or inadequate for safeguarding cyber physical systems, we can also see that for example, we can see the Ukrainian Stuxnet worm, and what that worm did was it targeted Siemens industrial software, and that was actually used to control nuclear fuel processing plants. And um, the the one of the adversaries could be other nations. For example, in the next slide we can actually see that there was an article which was published in Washington Post. It stated that Russia has developed a cyber weapon that can disrupt power grids, and it seems they have actually let people like cyber hackers try to deploy attacks or wreak havoc on the US power grid. And they have already tried this multiple times, it seems. So we know how important and how critical it is for a trustworthy operation of the nation's critical infrastructure. And that is why they need um, good security. So due to all these, we can discuss the impact of the Ukrainian Stuxnet worm attack. So in a little more detail, what the Stuxnet worm did, it actually exploited several complicated cyber attack vectors, and that included Windows zero-day vulnerabilities and logic controller exploits. As a part of that, they sabotaged and destroyed an Iranian facility. They introduced malicious control inputs to the actuators which were controlling the uranium centrifuges, and we know how dangerous that can be when they actually attack a nuclear facility. So due to all these, that is why these mandatory governmental regulations were actually embodied into the North American Electric Reliability Corporation um, Critical Infrastructure Protection, that is the NERC regulations. So these regulations were actually defined and they have now been widely adopted in the industry. So if you see the SIP, the Critical Infrastructure Protection, we can see that the latest SIP version 5, which was enforced on April 1, 2016, it actually called for increased strict cybersecurity requirements. The reason being to prevent adversarial power grid incidents by terrorist and targeted nation state intruders. As I mentioned, it could be funded by nation states as well. Another major SIP standard, which was guideline for electricity grid protection, is that the grid's real-time operation should always comply with the N-1 contingency resilience requirements. So what that means is for a power system with N components, components could be anything. For example, it could be a transmission line. The system, it must be able to tolerate any single component failure. So that is why they say N-1. Any single component failure. The failure could be anything, such as an overflow line outage, and this could be caused by malicious control inputs. So here, if we look at it, since the system here, so we here what we discuss is basically from a discrete incident to a continuous transient. So a discrete incident, it could be anything. So it could be like a fault, and a continuous transient could be a change in relays or change in any power lines or topologies. So if you see here, it's the transient dynamic attacks versus enforced regulations. What this paper has described is that the transient attacks, it doesn't, the enforced regulations, the NERC regulations, it doesn't take into account the transient dynamic attacks that happen. So they only monitor the steady state of the system. So there are steady state monitors, and what they do is the existing contingency analysis algorithms, they do steady state analysis. So if you see here the discrete incident, so here is where the attack zone, what they do is like they increase the frequency due to issues, the power generator frequency gets increased, and you can see that there is like continuous transients. So this is where the attack can be introduced, and that is where the NERC regulation zone doesn't come into play. So when we talk about transient stability, we have to actually discuss the equal area criterion. So here, if we see here that the y-axis has power and the x-axis has a lower angle delta. So here we see that there is an equation, m into d square delta by dt square is equal to ps minus pe. So if we look here, we can actually see that the PS is the mechanical power and PE is the electrical power, which is represented by the green, the orange, the amber, and the red lines. So the curves. So if we see here, we can actually see that when the load angle increases, the power, the electrical power decreases. So if we see that there is a TC, so when the TC increases, initially there is actually and initially the system might be operating at the delta zero, and then due to some falls, the power increases, and then you can see that it decreases. And here when A1, the region between the delta 0 and here the critical clearing angle. So when the load increases beyond the critical clearing angle, the system is said to be in an unsafe state where it can be detected. So here when the value of A1, the region A1 and the region A2, when the value is equal, we can say that the system is actually in an unsafe state. And when the maximum load angle increases, we can see that the electrical power after some time the system stabilizes and the value comes down. So we were talking that the system, the electricity grid, is vulnerable to transient state attacks. So that is why the question comes as to, is NERC standards effective? So if we look at non-compliant utilities, they are actually required to increase their system redundancy to improve the tolerance. Otherwise, they risk financial penalties by the government. So since they have to implement these requirements, they have been using various automation solutions, such as production relays to detect the incidents, like line current overflows. So since these utilities have been employed, you can see that these utilities have developed regular procedures such as contingency analysis to periodically validate the system resilience against failures. But the issue is that the existing contingency analysis algorithms, they leverage the power system to perform only a steady state analysis of potential incidents and their potential consequence. So what happens, the drawback is that this solution, it completely ignores the non-steady state or the transient dynamics of any system. They only consider the state where the NERC, we saw in the previous graph that the NERC regulation, that area, it contains only the steady state. So that means NERC cybersecurity requirements can be vulnerable against a new class of transient attacks, and hence we believe that they are inadequate for protecting the national electricity grid from dynamic transient exploits. So this is why we came up with an algorithmic approach for the synthesis. So if you see that synthesized attacks against the SIP compliant power networks can cause global system level collapse or instability. So if you see the attackers are becoming smarter day by day, we can see that transient attacks should be taken into consideration also for the design of any future protection mechanisms. So our synthesis procedure, it leverages hybrid models of the electricity grid that incorporate not only the continuous nonlinear dynamics of the electrical quantities like currents, voltages, power, and phase angles, but also discrete dynamics of the changes in the network topology brought about by opening and closing of relays and changes in power consumption. What that means is it just doesn't consider only the steady state values such as currents, voltages, power, and phase angles, but also considers changes in network topology, which I believe was not being considered. So the synthesized attacks consist of a sequence of malicious control actions. So what they do is they ensure that all the behavior of the system, it remains undetected by the conventional steady state monitors, but they actually ultimately destabilize the system. So uh, the whatever changes or attacks that are being targeted at a system, they go unnoticed by the steady state monitors. So our goal is to automatically synthesize such destabilizing attack over a specified bounded time horizon, such that it happens within a time frame, so that the SIP protection monitors or mechanisms are not triggered. So what that means is we need a parameterized attack space. We will discuss that in detail a little later. So here with the parameterized attack space, we can see that the proposed algorithm, it uses formal verification algorithms to search the space for successful attacks. And the key is that they should be quickly able to eliminate parts of the attack space that cannot produce successful attacks. That is because they are detected or because they are unsuccessful in making the system unstable. So we generally avoid the area where it actually has the successful attacks can be detected. So this algorithm also eliminates sets of unsuccessful attacks by first simulating one potential attack. So we can actually discuss this, go to the next model. So to implement our attack, we are using the threat model as a SCADA network. So we all know what a SCADA network is. If you look here, we can actually see a SCADA is a supervisory data acquisition and control network. So what it actually does is it was used for a formal hybrid system. So in the SCADA network, we are using SCADA network as uh, a model, and it is usually used to monitor and control a power system and devices in a geographical area. So the SCADA network is connected to the physical power system components. Through, you can see that there are actuators, and there are also, they have sensors as well. So they have distributed sensors and actuators. So if you see the daily operation of a power grid, it usually follows a typical closed loop monitoring, and it also actually has a control paradigm. So the sensors, if they detect any noise, they send it to the SCADA network. Since the SCADA network does continuous monitoring, it has a close and constant interaction of the physical power system. So electricity grid is referred to as a cyber physical infrastructure because of that close and constant interaction. So you can actually see here that electricity grid as to how it is interacting with this network, and how we are exploiting or creating a malware is we use power system continuous dynamics and discrete logic for topology reconfiguration. So basically what that means is we are using a hybrid system automaton, which we will discuss in some time, and which has a verification and synthesis. This in turn creates an embedded malware, and that in turn is exposed to the system. So if you look here, you can see a hybrid automaton. So a hybrid automaton, I can give an example of defining a hybrid automaton. You can see here that um, there is this is a thermostat. So a discrete event here, a thermostat, it based on the times, the temperature. Here the temperature when is lesser than 65, it actually goes to, there's a state 1 and state 2. If it's, when it's greater than 75, it goes back to state 1. So this is a discrete event where it actually has a sensor for temperature, and it works accordingly. And that is that is why it is called a finite state machine, where you define between 65 and 75. A continuous event, here a continuous dynamics is where, like a heater, where you pass in a temperature and it's continuously it's heating, and it doesn't have any excuse me, it it doesn't have any states defined. So a finite state machine plus continuous dynamics lead to a hybrid automaton. So you can see here, when both are combined, when the heat when the temperature is lesser than 65, we see that the heat turns on, and when the temperature is greater than 65 75, it goes back to turning the heat off. So this finite state machine and continuous dynamics together make up a hybrid automaton. So here we can see a change in discrete events. Here, what that means is we can see a 3-bus system where it has 3 buses, bus 1, bus 2, and bus 3, and it has generators, and we can see the network topology between them. Here in topology 1, we can see that line between bus 2 and bus 3, they are open, and here we can see that the line between bus 2 and bus 3 are actually closed. So this you can term as a change in discrete event. So coming to the hybrid automata model. So here, as we discussed earlier using an example, here it actually has theta and omega, where theta is a synchronous phase angle, omega is the angular velocity. So it takes into consideration all these values, the real valued continuous state variables, the discrete variables where it has a mod on timer and um, on and off, and it has relays. So this can be termed as hybrid automata model because it has a set of possible discrete transactions, theta set of initial states, t set of state transition trajectories. So all these variables make up the hybrid automata model that we are defining. So now we come to the attack synthesis approach. So what the attack synthesis approach is going to do is, it actually is the transient attack synthesis problem. It is done using the reachability problem. So the reachability problem that we are discussing here, it's based on the semantics of the hybrid automaton model, and that is defined by the runs divided by the execution, and that has a finite sequence of trajectories. So the key is to parameterize the space of attacks, and then search for successful attacks by eliminating parts of the parameter space that cannot yield attacks, as we discussed earlier, which cannot have successful attacks, or which can already be detected. So what it does is, like, we first do a single attack, and then we also check the reach. So this is the algorithm that was discussed. So if you look at this algorithm, you can see that the input to the algorithm here is actually automaton model, and then you can and then you can see the discrepancy functions for the different modes. You can see the unsafe set and unsafe, which is in the asynchronous state. You can see the detectable set, detected, and the time horizon T max, and you can also see the set of parameters P. So the algorithm, it maintains a data structure S, and which is a cover of the parameter space P. So S is a collection of pairs. So it actually, here if you see, S is a collection of pairs of P and E. So the compact parameter space P is contained in B of Pi EI. So if you see that for each parameter value Pi EI equal to S, so the algorithm must first simulate the system with parameter Pi to generate one execution alpha of Pi, and it should be of duration T max. So that's the simulation which is done. It then uses the discrepancy functions to compute the set of states R, and by plotting alpha. So if you see from the property of discrepancy functions and argument presented, we know that R is an over approximation. So here if you see in this, you can actually see that if there exists a time t at which the reach set R of t, it is R of t from the parameter range is contained in that unsafe set unsafe, and for each t less than t max, if this condition holds, then the parameter pi yields a successful attack. So one that reaches unsafe. So, and while avoiding detected. So you can see the transient attack parameter space where it switched transient attack parameter space where a sequence of attack modes A of 0, A1, A and minus 1 and the sequence of time points. So if you see here, you push the system to a transient state without being detected. If you see here, this is the attack zone and then you push it without being detected. So the attack on maximum input power. So in a normal scenario, if you have the maximum input power, it will actually be detected by the steady state monitors. If you see here, based on the phase angle and the time, if when the time increases in that state, you can detect it. But the attack was simulated using a PID controller. So in this case, the attack will not be detected. So here, the critical time, they did it in, we mentioned that there's a time bound horizon, and in that time frame, they actually launched the attack. So we can see a 3-bus system attack. This was the results of the transient attacks. So you can see that here the unsafe state, there's a critical angle, and then when the phase angle value is beyond the critical angle value, we can see an unsafe state being reached. And here we see successful transient attack against a power generator. You can see that when the generator rotor angle, it falls out of step, it destabilizes, and you can see that the generator's output electrical power, it becomes unstable, and we can also see that the bus frequency cannot regain stability. So when in the unsuccessful transient attack which they did, it you can see that it stabilizes safely even after a sequence of relay switches. And here the output electrical power also stabilizes and where it was detected, and the power bus frequency also stabilizes. So coming to the conclusion, we see that the algorithm, it demonstrated that the NERC requirements, it can fall short. It proved that it can fall short in protecting against malicious adverse parities, and we used experimental results that show that the non-steady state system transit dynamics, it actually enables attackers, and it was not detected by NERC standards. So the solution here is NERC should have transient aware contingency analysis enforcement, and we should use more fine-grained monitoring of system transients, and you can use algorithmic attack tool as a contingency analysis technique, and that would guarantee system security against transient attacks. Any questions, kindly forward it. Thank you so much for listening to my presentation.